Okay, so I hope everybody had nice chats and some networking over the break here. We'll get started with our next session. We're slightly behind time, apologies for that. But so our first session, we heard experts from North America, and our second session, we'll hear two experts who are currently doing things in European markets. And we'll start out with Filip Jorissen. So Filip, take it away.
Okay, hello, good morning everyone. I'm Filip Jorissen from the company BuildTwins. That's a company that my associate and myself have founded 2 years ago. And we work on model predictive control for building applications. That's at least initially what we started out with. In the meantime, it has expanded a bit. And this is based on research that we started in 2013 as PhD students at KU Leuven. So we've got a very long research track past us between the two of us. So me and my co-founder both have a PhD in the group of Lieve Helsen. And what is a bit peculiar about what we're doing is I think we're still one of the few companies or just people implementing MPC who use white box models, so physics-based. Especially now with the AI era, this is perhaps a bit weird, but we think we have good reasons for doing so. And today I would like to bring a presentation that again goes a bit into that, to give some arguments and insights based on what we have learned, and especially now with new business cases arising, to show how this really matters. So I'm not going to give a lot of details about case studies. In my opinion, that whether you get 10 or 15% savings doesn't really matter. The thing is whether you can implement that systematically in a commercial context, which is a completely different type of question. And that's something that we most struggle with, much more than the algorithms nowadays. So let's get started. So just some context within Europe. As you know, we're all trying to avoid climate change. We're trying to have less carbon emissions. There are big plans for that in the EU as well. The Fit for 55 program essentially tells us we have to reduce emissions, but due to that, a lot of things are changing right now. One of them is that there's, of course, a push for more efficient use of energy, so the efficiency that we do use to use it more efficiently. That leads to more complex HVAC systems, for instance, heat pumps, etc. Or multiple devices combined, and you can switch between them. We will have, at some point, time-dependent energy prices. There's integration with electrical systems like electrical vehicles, electrical batteries, PV systems, because you can have efficiency gains there as well. And we're seeing as well that with all the new technology coming available, people do expect better comfort. So the control problem that we initially started from 10 years ago and then even decades before that, it's becoming increasingly complex. And we need a scalable solution to work with that. But in addition to that, there's a design problem. So the question is, how do we design our buildings with all this complex stuff that's quite expensive, by the way, all the heat pumps, chillers, etc., not just to operate them, but also to buy them. How do we size buildings in the future to do that in a way that minimizes the total cost of ownership? Secondly, I mentioned already the control problem, which is given a building design. So once the building has been constructed and it's there, how do we operate the building every hour or every 50 minutes or every minute? So how do we set points for actuators to get the least energy use possible while still maintaining thermal comfort? Now, what's often, in general terms, speaking in general terms, what is often done is an approach which is the following. One, we define a solution space. So in the case of design, you have multiple design options, for instance, sizes, etc. And we're going to make a digital model of the problem that we're trying to solve. We evaluate many of those options within that solution space, and we take the best one. That's a very high level approach that very often is being used. So that's what I'm starting from. So suppose we apply that to the control problem that I just mentioned. What happens is that given a building design, so this is for one specific building, one approach to actually dealing with that is that we have some model, let's call it a digital twin. It has some control inputs, and it has an energy cost that comes out. And an important thing not to forget is that there are also boundary conditions, because if these weren't there, then yeah, you could solve this once and you have your optimal solution for always, of course. And what we then do is often we send multiple inputs here, multiple energy costs come out, and we take the best one. So I guess these are not very complex concepts. But the question now becomes, how do you make that digital twin? Because I said, okay, we have this box here, where does it come from? That's really the key question, I guess. And what we see often being done, especially in data-based research, is that this goes as follows. So there is, for instance, a physical building. So there is an actual building there, which generates a lot of measurements. These are collected in a data set. And that data set then controls these different aspects that we had before. So the 3 arrows here, all of them, they are combined in that data set. We give that to some system identification algorithm. It does a lot of math on that, and out comes the box. That's the idea. That's, broadly speaking, you can apply this to different type of problems as well. Some of it in the presentations today. That's what we're talking about. Now, there are some problems with that approach from our perspective. One, the measurement availability. And quality as well. I'm sure many people who are in the field, they are aware, okay, sensors can be broken, but you can clean it up and things like that, but you still have to do it, of course. In some cases, it's not possible. It may be only after the facts that you see you've been measuring for 1 year, and then suddenly you see, ooh, damn it, these sensors are broken. Then what? It's really not just a practical problem. Once it's your business, this is really a big problem. We have a competitor that we hear from our clients that are working there. They are measuring now, and in 1 year they will start doing trials. And we're like, yeah, okay, good luck with that. Let us know when it's done, but we can be up and running in 1 month. So it's not a little detail. Other things is that in new construction projects, there are no measurements. The building is not physically there. You can't have measurements. So such a methodology does not apply. And even if you have measurements, the question is how many do you need? Because if it's 1 year, 2 years, 3 years, I don't know myself, I'm not very active there, but I can imagine even getting enough measurement data is really prohibitive in practice for more complex control problems. Then, suppose you do have a measurement data set. That data set has been collected for a specific set of boundary conditions. Boundary conditions can be the weather, but it can also relate to different time of use pricing. So the model is only trained then within that data set that's available. Suppose that there's, for instance, a very warm day, but there is only one very warm day in your data set. Chances are that it's not very well calibrated for that, and you will run into trouble. Other things is that the design can change. Quite often we have a hierarchical sort of controller where there's an MPC on top of something and there's a rule-based controller below it, and the MPC gives set points to the rule-based controller. Now what happens if that rule-based controller suddenly changes? Someone changes a set point, the heating curve changes, or whatever. Something changes to the rule-based controller and suddenly your trained model, which you waited 1 year for to get, is out of the window. So things like that, also renovation, for instance, there is new glazing installed in the building envelope. Suddenly your G value is only half as much. You get a lot less heat inside of the building. Or there's COVID. Suddenly you have to open all the windows. Training-based models, they're not really, by design, designed for this. And it's these kind of things that simply are not detailed. So that was a control problem. Now, if we try to apply the same reasoning to the design problem, then of course this becomes even more difficult because we can't have measurements of multiple. We can't build like 10 buildings to see which one is the best, right? So that doesn't really work. And a second thing here is that there are multiple use cases. So in this case, we have a control problem and a design problem. And suppose you would have these different flows going through them, then you get a digital twin, one for the control problem and a second one for the other. But they're not really consistent because you use different data sets, so you can't really make those work together inherently. And you might say, yeah, why do you need that? But suppose that we're looking a bit further than just control and design, but we also have building lighting that you want to somehow train and optimize. You've got fault detection that you want to do, maintenance, etc. If all of these have different data sets and they're not inherently designed to work together, then you start having different products that live by each other, perhaps in different companies, and then they have to interface at some point because the lighting affects how much heat is introduced into the building, the design affects what control options are there, and all of that becomes very complex. So the question really is how can we do things better? So if you go back to the previous explanation, so this is what we don't want to do, and instead what we would like to have is a different digital twin that has inputs for all the type of applications that we like and outputs for all these applications. And then depending on the use case, we select a few of them, but in any case, we always have the same model underneath. So for a control problem, we can use control inputs and the energy cost as an output. For a design problem, we have design inputs and optimal design. And now when it really becomes interesting is when you start combining some of them, of course. So suppose you want to design a problem, a building, but the question then is how do you control that building? If you have multiple designs, yeah, how do you design a decent controller for all those different cases? And then you can use optimal control for that specific design and do an overall optimization that takes both effects into account. And then that's when it becomes really interesting. Because, for instance, with the heat pump that costs, I don't know, €500,000 for a large building, you can say, okay, we're going to halve that size and tell MPC, this is what you have, deal with it. And it will start preheating and things like that, just to make sure that comfort is still there in that one day of the year where that you actually need that peak capacity. And that allows you to save a lot of money. So how do you create that digital twin? So again, rearranging inputs and outputs, you would need a data set from measurements or something else that combines all of these things. Clearly, I don't think this is a type of research that's typically being done. Such a data set would be huge. Also combinatorially, because you need all different combinations to be able to train what will actually happen. And then that's just for one building. Every building is different. You would have to redo this for every different building. So that's not really how we want to go. So how do we do it? One step back, there is a thing called building energy simulations. It's been around for decades. And most of that, these inputs are already present for a building energy simulation. You've got sort of control inputs, design inputs, boundary conditions, and outcomes energy cost. And if you run multiple loops on that, you can get an optimal design out of it. So what we do is very like that, but it's a more, let's say, advanced version of building energy simulations. So how we create models is we start from the building as built file. We've got schematics, technical data sheets of individual equipment with parameters like UA values, nominal mass flow rate, COP, etc. Architectural plans for the size of zones and location of walls and things like that. We map that into a Modelica model. And in doing that, we instantiate a whole bunch of devices and components that declare control inputs. And the design is imbued in this model. And for instance, this heat pump component model can have a parameter for the nominal power. And this can then be changed afterwards to run different designs. We have a toolchain that takes that Modelica model and maps it into an optimization code. So it's nonlinear, mixed integer nonlinear programming. And once we have that code, we can run it for the different inputs, given some boundary conditions, and then evaluate the various objectives that we have. Now, what can we do with that? Some applications where we use this framework. I think I mentioned most of them before. Optimal control. So in this case, we have a fixed design. The design is known. Boundary conditions are known, or at least they are weather forecasts. And then the controls are optimized, and we achieve optimal energy use in doing that. Second thing is control integrated design. where we evaluate multiple designs for which the boundary conditions are again known, for instance, 1 year of meteorological data, and we optimize the controls and find an optimal overall investment cost. A third application that we do is fault detection, analogously. Some inputs are fixed, some are free, and we run with that. So I'm going to go a bit into more detail in a few of those cases. Just for those who are not aware of what model predictive control is exactly, the idea is that if you compare this to typical rule-based control, hysteresis controller, we typically say it just looks at the position now. And if we cross a border, so suppose this is a racing track, this is a race car, you keep on going straight until you cross the border, and then you take a control action. And then in doing that, you bounce off the track, and okay, you will eventually get through the track, but it's not the most efficient way of doing that, of course. A PI controller can be considered to be a little bit more intelligent. It tracks the center of the road, and each time you diverge from that center, you try to take corrective action to follow the center. And rules are some things that, like a signpost by the edge of the road, that gives you a clear instruction: when this happens, do that. And a rule-based controller of a building essentially combines all of these, but at each moment in time, it looks at now. It doesn't look into the future. And that's what a big difference with model predictive control is. We have a forecast of the building, what will happen in the coming 3 days based on that model. And we will see that if we want to take this corner over here very steeply, we have to take this turn here, and then we can find the largest speed possible without losing traction here or here to be able to get through the track. So that's a bit the rationale behind what model predictive control is. So we have applied that years ago in our first case study, which is the office building of Boydens and Fluvius, Boydens and Sweco. So Boydens Engineering is a company we have collaborated with, developing this technology, and this was their main office, which is, in the meantime, it has been bought by Sweco. And what we do there is we provide set points for all the HVAC equipment. So there is a heat pump, concrete core activation, air handling unit, and VAVs. And we have achieved 35% energy savings there. This is a scatter plot with energy use and outdoor average temperature. One bullet is 1 day, and you see that the blue MPC dots, they are systematically much below the reference line of the rule-based controller. Now, in this case, how do we do that? There are, this is a HVAC schematic, and the tricky bit is here that we're actually controlling 6 various different devices to be able to achieve this. I can't go into the details now, but there are VAV dampers for which we control the flow rate. We control the heating coil to heat one specific zone a lot using that heating coil, due to which the air handling unit can have a lot lower supply air temperature. And we need to use more the concrete core activation to have enough heat in total for that one specific zone that's being too cold, and then the temperature of the heat pump is adjusted to be able to get that peak power here. So actually we're using relatively high temperatures. But the fact that we're not heating the whole building and just one specific zone, at the end of the day, saves us a lot of energy. Another application is currently we're working on a research project, a Horizon Europe research project called SEEDS, where we're controlling a district heating system of 12 individual small houses called as HIPjes. So there's a geothermal heat pump, one central geothermal heat pump. There are individual booster heat pumps in the individual houses, and there's a low temperature district heating system between them. And we're doing optimal control, and we will do model calibration based on that side. And the goal of the project is really to look towards, in this case, cultural heritage to be able to renovate these kind of cases. This is a case where we have been working on fault detection. This is the Herman Terling building. The Flemish government is in this building. It's in Brussels, 50,000 square meters or 500,000 square feet for those who are more used to imperial units. We have 1,000 control inputs in that model and about 500 zones that we're controlling. And by going through all these various actuators, etc., we identified many faults and also many different types of faults that we're still resolving now before we can actually start operations in a reliable manner. For the control integrated design, there was design study that we have done, where the question was, okay, we have this building, we have time of use electric pricing, and we want to install a thermal energy buffer to shift load to that buffer to reduce the overall energy cost. And I'm like, that's great. That sounds very interesting. We're going to save a lot of energy in doing that. But then doing the simulations, we found out that actually it doesn't change the energy use all that much, just by a few percent. And we were like, something must be wrong. And we digged into the results. And it turns out that because the thermal mass of the building envelope is so much more than those tanks, and we're talking about 50 cubic meters, but the equivalent tank size of the building envelope is 1,800 cubic, no, it was 200 times more. So the tank size is still negligible, and MPC could already store energy in the building envelope. Okay, it could do it slightly bit more efficient with less heat losses in a tank, but it didn't make all that much difference. And that's also, from a research point of view, very interesting, because many research studies on tanks, they happen with demand profiles. They consider the building load to be inflexible, which is not the case. So all those studies are wrong, to put it like that. It depends, of course, what the thermal mass of your building is. In Belgium, we do have relatively heavy buildings, I think, compared to the US, so maybe not be the same, but it's really interesting things that come out of doing those detailed simulations. So what we have here is the energy use throughout the year, and yeah, especially with these slides, there are four lines here, but 3 are so exactly on top of each other, actually. You can't even distinguish it on the slide. Oh, here you can see it a bit better, perhaps. Second application is where we're looking towards a retrofit of a building, large office building, and they want to know how much the energy use will be after renovation. So we're looking at chilled ceilings, VAVs, chillers, air, water, heat pump, humidification, and dehumidification on the air handling units. So all of that is in the model. And we were asked to assess the peak power. So how much power will we need to run that system? And also the overall yearly energy budget. And I'm not going to present those results, but one thing that was very interesting that came out of this is that the cooling coil of the air handling unit was being used to heat the air. And initially you're like, yeah, but that must be wrong. But so you can see the power through that heating coil. And in summer, it's really negative and very large. But throughout many other parts of the year, it's positive. And what's happening there is that MPC is disabling the heat recovery of the air handling unit. It's drawing heat from the chilled ceilings, passing that through the cooling collector to the cooling coil, and preheating the air using that heat. And in doing so, you don't need a chiller to run to cool the various zones that need a little bit of cooling. And instead, you can use just a bit less heat recovery. And it's these kind of things that, if you have detailed models, they just naturally arise. This is something that in a linear model, you would not even be able to model, I think. Because the delta T's, you can't put that into linear constraints. You need nonlinear models to be able to do that. So that was a really interesting side effect, and now we're thinking, how can we actually do this? Because rule-based controllers typically don't allow for these kind of things, so we really have to think about what to do with that. Another control integrated design. So the case we were running now, I think it was about, the one I mentioned was 60 zones, and we have about 28 million state variables there over the year. And what's now next is we're trying to really, perhaps we're overdoing it a bit, but a client had a question for a model of 600 zones to do a full year simulation, so that would come to a model with 3 billion algebraic variables. Just to make that clear, these are really huge models, and that's what we're currently working on to make this possible through parallelization, etc., on a computer. So one of the final slides, I think what I wanted to show a bit is that we can really benefit from having the same model for the multiple approaches. And you also see that during the building life cycle, where you start from design, build, control, maintain, and retrofit. And in each of these steps, you can use such a model for different applications. And it really helps if you have to make the model only once. But what helps even more is that you can have corrections at this stage that affect the model and that are eventually resulting in benefits here, or vice versa. Or you find something wrong during maintenance, again, that you can feed that information back into the model and the control adjusts. For instance, if a valve is broken or stuck, that you can tell the controller, this valve is broken, you can't use it, and then it will work around it. But if you have different models that are not standardized and no way of collaborating, you can't do these things. What's also interesting is throughout this process, if you find some clear emergence of whatever mismatch between a model and reality, that you can see, our cooling coil model for condensation of moist air is not very accurate. It seems it's always in this case, and you figure out what's wrong, you update the model, and then you can update that for all your buildings at once because they all use the same framework underneath. So software updates and things like that become very powerful as well. So, to summarize, we developed a framework for integrated design operation of building energy systems. The goal is to come to globally cost-effective solutions, but also to something that really works and is scalable and it's robust. If there is a problem, like I mentioned before, if a valve is stuck, you can do something with that. You're not suddenly in a situation, now I have to turn it off because the other valve is stuck, and things like that. So, and we're leveraging physics-based simulation models to be able to do that. I also would like to thank various partners that have helped us in the past, and funders, including the European Union. Voila, thank you very much. Any questions, please?
All right, I think we have time for one quick question. John?
Thank you very much. Question on your physics-based simulation. Can you describe the physics a little bit? Is this an energy balance? Are you doing a CFD, finite difference calculation under the hood? Is this an RC model? Describe the physics in your physics-based simulation a little bit.
Yeah, sorry for taking too long, by the way, apparently.
I started you a little bit late, that's okay.
So we use Modelica models. This is a graphical representation of that, and essentially each component represents a set of equations underneath. For instance, in the case of a heat pump, there is a model that has the typical relations between COP, condenser power, etc., and then an efficiency curve based on temperatures. For a pump, it's delta P times volumetric flow rate divided by efficiency, these kind of things. For the building envelope, we use what are effectively RC models, but quite detailed. It's models from the IDEAS library. They have been published and documented, so all the equations are publicly available, and the library itself is also available. So these are really basic engineering equations that are very well known in most of the cases, and in some cases, we go a bit further, like modeling moist air, etc. That becomes a bit more technical already.
Okay, I know I have about a half a dozen questions for you myself, and I'm sure there are many others in the room, but hopefully we can chat a little bit offline. So thanks again, Filip. And our next speaker is Alfonso Capozzoli, who will join us from Italy, and he will be presenting on Zoom.